Have you ever looked at a really complex math equation and just seen, well, a total mess of numbers and letters? What if I told you that hiding inside that mess is actually a simple, beautiful shape, just waiting to be seen? Today, we're going to learn the secret to unmasking them. So let's just jump right in. On the left, you see the equation for a circle. It's clean, it's simple, we all get it. But on the right, whoa, that looks like a totally different beast, right? Well, believe it or not, that messy thing also describes a simple, elegant shape. The real question is, how on earth do we see it? And that is our mission for this explainer. We're going to solve this exact puzzle. We're going to see how a simple change in your point of view can transform total mathematical chaos into something with beautiful clarity. Okay, so to get started, we need to understand the blueprint for these kinds of shapes. It's something often called the tilted curve problem. This monster of an equation you see right here, this is the general form for every conic section. We're talking circles, ellipses, parabolas, you name it. They all fit this exact pattern. The specific values of A, B, H, and all the others are what determine which shape you actually get. So let's break this down and find the parts that are causing all the confusion. The terms that have just an X or a Y, those are our first clue. They're telling us our shape isn't sitting nicely at the origin. It's been shifted somewhere else. But the real troublemaker, the one that makes it so hard to recognize, is that XY term. That's the smoking gun that tells us our shape is tilted or rotated.
So, how do we fight back against these troublemakers? Well, we need some tools. And our first one is all about shifting our point of view. It's a process called translation.
Before we get into any formulas, think of it this way. Imagine you've got a big map laid out. Instead of moving the map itself, you just take a clear piece of plastic, lay it on top, and draw a new center wherever you want. The map didn't change at all, right? Just your frame of reference. That's exactly what translation is. And here's what that looks like on a graph. We start with our original center point, our origin, O. Then we just pick a new one. We'll call it O prime, at some point, alpha, beta. Notice, we're not tilting or turning anything. We're just sliding our whole grid over. And these are the simple formulas that let us do it. By plugging these into our big, messy equation, we can choose our new origin, O prime, so perfectly that those pesky X and Y terms just vanish. We've basically recentered the whole shape. But, translation only solves half the problem. The shape might be centered now, but it's probably still tilted. To fix that, we need our second and even more powerful tool, rotation.
The source material puts this perfectly. Getting rid of that tricky XY term is the same thing as rotating our whole point of view until our grid lines line up with the shape's natural tilt. The solution isn't to change the shape, it's to change our perspective to match it.
Visually, it looks just like this. We keep the origin in the same spot, but we pivot our entire coordinate system by some angle, which we'll call theta. The whole goal is to get our new X and Y axes to line up perfectly with the shape's own lines of symmetry. And yeah, you guessed it, we've got formulas for this too. Now, they might look a little more intense, but their job is incredibly powerful. When we plug these into our equation, we can figure out the exact angle theta that will make that pesky XY term disappear for good. All right, theory's over. We have our tools. We understand the concepts. It is time to go back to that original mystery equation and put all of this to work. Here it is again in all its messy glory. Now remember our goal? We're going to transform this into something clean, something simple, something that tells us exactly what shape it really is. And we have a super clear two-step plan. First, we're going to slide our perspective to center the shape. That's translation. Then, we're going to rotate our view to align with its tilt. That's rotation. Let's see it happen. So after applying our translation formulas, poof, the X and Y terms are gone. Look at that. The equation is already so much simpler. We've found the shape's center, but that XY term is still there, telling us it's tilted. We've got one more step to go. And now for the really cool part. We apply the rotation formulas, we find the perfect angle to line up our view with the shape, and that XY term just vanishes, finally revealing the true form of the equation. And there it is, an ellipse. That's all it was. All of that complexity was just a simple ellipse that had been pushed off center and tilted.
This final equation is clean, it's recognizable, and it describes the shape perfectly from its own point of view.
Okay, so let's just stop and think about what happened here. We changed the equation by changing how we looked at it. But did we change the shape itself? No, of course not. And that leads to a much deeper and honestly really cool mathematical idea.
This brings us to the concept of invariants. These are these fundamental properties of the equation, certain combinations of the numbers that do not change, no matter how you rotate your perspective. You can think of them as the shape's true DNA. And this table just proves it, plain and simple. Take a look at the trace. That's just the sum of the coefficients on the squared terms, and the determinant. Before we rotated anything, they were 13 and 36. After we rotated it and the individual numbers changed like crazy, those two core values stayed exactly the same. They are invariant.
And that is the big takeaway here. Translation and rotation don't change the object itself, they just change our description of it. By finding the right perspective, we can make that description as simple and as elegant as the object truly is.
Which really leaves us with a final thought, and it goes way beyond math. If a simple shift and a turn can reveal such profound clarity in an equation, just imagine what other hidden truths and simple structures are just waiting to be discovered. In science, in art, maybe even in our own lives, if only we're willing to change our perspective.